Hello there, my name is Bob Oblack. I've been involved in fluorescent minerals since 2013. I attended the Tucson Rock and Gem show back then and decided that I wanted to learn more about this hobby called fluorescent minerals. And here we are in 2025, and I'm making this presentation for a YouTube video. And it's all kind of, for me, it's all about the science. I'm kind of a nerd when it comes to understanding why things work. So today we're going to talk a little bit about the science behind why these minerals will glow in the dark. And so let's get started. It's all about color and energy. The these two words just exude the fact that you see all these different colors of the rainbow, but what causes it is the energy that we put into these rocks. So first of all, let's talk a little bit about color. Color in our everyday life, without looking at minerals with UV light, we see light reflected. And what happens with like this photograph of a malachite on some amethyst. You see the green malachite mineral and it's reflecting green. What happens is that all the colors of the rainbow are absorbed in the mineral, with the exception of the greenish colors that you see coming bouncing back to your eye. The same thing happens in the springtime when the leaves grow out, fresh leaves grow out. You have chlorophyll in the green leaves, and all the colors of the rainbow are absorbed by the leaves, and the chlorophyll color of green is reflected back into your eyes. So we see color through reflection. And as those same leaves in the fall will turn orange and browns and reds, the green chlorophyll disappears when it gets cold. It dies off, and the base leaf then gives you all the colors that you see in the fall time. So color for us in our everyday life is color from reflection. Let's talk a little bit about energy now. As we live in this, in our everyday lives, we can talk on our cell phone, and in our cell phones, we have radio waves. And in our microwave, we have energy waves that are even higher energy than the radio waves. And in this particular graph or slide shows energy from left to right, with increasing energy as we go farther and farther over to the right-hand side. You know, as X-rays, we can see our bones through our body, and gamma rays, those are caused by supernovas exploding in space, and they create tremendous amounts of energy. We'd vaporize if we got in front of a gamma ray burst. But down here, about in the middle of the energy spectrum, is our visible light spectrum. And our rainbow that we see when the sun shines through a rain droplet and we see this beautiful rainbow, we're actually seeing an energy spectrum from red to violet. You can see the rainbow colors here. So this is a spread of energy that is in the form of colors, because our eyes are tuned to this part of the spectrum. We can't see radio waves and we can't see X-rays except when they're developed on a film or in some technology that today is digital. But anyway, we're seeing our eyes pick up the frequencies of this energy spectrum. And to the right of the visible spectrum is the ultraviolet spectrum. It's right next to the violet part of the rainbow. And in our hobby, we have three wavelengths: long, medium, and short. Long being the least amount of the UV energy part of the spectrum, short being the higher part of the energy spectrum. So when we put an ultraviolet light on our minerals, we're putting energy on our material that we're looking at in the form of these different frequency wavelengths. We call these UVA, UVB, and UVC in our vernacular for our hobby. So let's talk about another energy called the law of energy. This is a law that is Well, it's kind of the guiding principle by why we see our minerals glow in the dark. And this law of energy is like the law of gravity. If opposite materials, opposite mass will attract each other. We drop a flashlight from our hands, it goes to the ground. That's the law of gravity taking over. And the law of energy, it says we can neither create it nor destroy it. We can transform the energy, for example, from chemical to motion. Like when you go Halloween trick-or-treating, kids go out and they eat a bunch of sugar and that turns into energy in their body and they get all excited. Same kind of concept. You're just transferring the energy that was in one form into another. So the law of energy says you can't create it, you can't destroy it. Scientists call it the conservation of energy. So let's now look about how we get light. We can get light from either heat, which in this case, the sun, just a huge hydrogen gas encased into a huge mass, and it's creating light through heat. Your ordinary light bulb, before we got LED light bulbs, the tungsten filament would be heated up and it would glow very brightly. So we call this incandescent light. Now, another kind of light is luminescent light. This is the light that we see from our minerals when we put energy on them or a UV light on them. Luminescence is light that can be created at very low temperatures. Actually, there's really no temperature increase when we're putting a UV light on a mineral. There might be some, but it's so insignificant it isn't even measurable. So we have incandescent light and luminescent light. Luminescent light is really fluorescent light. We're using the words interchangeably. So when I have a rock like the one here pictured, an ordinary light, it's reflecting brown because all the other parts of the rainbow are absorbed by this rock, and we see the brown content bouncing back to our eyes. And then when we put ultraviolet light, we get all these colors. And so this rock that was once brown, invisible light, when you turn the normal lights off, our white lights off, and you expose this rock under UV light, it actually radiates energy in the form of visible light. So it's actually luminescing. And we'll talk a little bit more about how that all works. But first of all, I want to review the concept of energy one more time. So what we're doing is putting energy, which is from a light source like this handheld portable UV light from UV systems, and all our materials that we're looking at, whether it be a rock, crystal, or some other item like a piece of glass that might have some impurities in it, there is a structure to that item, and here's an atom, nucleus with energy shells orbiting and surrounding the nucleus. When I put energy on the rock, let's say, I'm imparting energy into the electron cloud, and that energy is absorbed, and that energy of that electron cloud goes to a higher energy shell. It's very unstable out there. This is a form of ionization, they call it. And so when it's out here in this unstable high energy state, it doesn't like to be out there. It wants to go back to its grounded state. But because of the law of energy, that electron, when it goes back to its lower energy shell, it emits the energy that it absorbed in a longer wavelength. This is the principle of electron displacement. And there was a gentleman by the name of George Stokes, and he discovered this principle in 1852. So let's kind of review what we're seeing here. We're using the law of energy, where that electron absorbed energy. It was unstable in a higher energy shell, then went back to the lower energy shell. It's transformed its energy back, and it released the energy in the form of visible light. So let's look at this energy spectrum. Here's the energy that we put into the light. Let's say it's a short wave. That's UVC, and it was 100 nanometers to 280 nanometers in length. That's the wavelength of that energy spectrum. So I put that energy in. It was unstable. It went to a grounded state, back to its normal grounded state, and it released energy in this visible spectrum. That's why we see color coming off of the rock. We're putting energy in, and it's releasing energy in the visible spectrum. It's called electron displacement. It's pretty simple, but there's some laws of energy that take place here. The law of energy says you have to conserve, you can't create it, can't destroy it. I put energy in, I'm going to get energy back out, and that energy is released in a longer wavelength. There's a very small amount of heat that's also released, but mostly visible light. Okay, so let's talk a little bit about how and why these minerals will fluoresce. It's not all minerals will fluoresce. There's about 15% of our minerals fluoresce, and there's about 3,600 minerals that have been identified totally. About 500 of them are known to fluoresce. You can have the same mineral, let's say fluorite, and not all fluorite will fluoresce. It requires an activator or an impurity, specific impurities that will cause the fluorescence phenomenon to take place. And you can't have too much of those impurities, less than 3%, oftentimes, a hundredth of a percent. So with the presence of the activator and the presence of the particular mineral, of which we have about 500 of them known, the combination of the activator and the right mineral, we get fluorescence. Here are some of the activators that are known to cause fluorescence in our samples that we see on display, that we have in our fluorescent displays. So this was originally discovered by Stokes. He coined the term fluorescence when he was looking at a mineral, fluorspar or fluorite, and he used a light tube. And this light tube was in a. He first had the window in his lab, this light tube to the window, and then down towards the bottom of his floor, he had a long tube, and all of the white light, the visible light, disappeared as it traveled down the tube, and only the UV light struck the mineral. And as he was looking at fluorite, he says, "Wow, I see this mineral is glowing blue. I've got to call this something." So he called it fluorescence, from the mineral fluorite. Now, what is fluorite? Well, it's calcium fluoride. So calcium fluoride, CaF2. But in the case of the mineral that fluoresces, so not all calcite, or not all calcium fluoride or fluorite will fluoresce. It requires an activator. In this case, europium is usually what's present. So it's the combination of the base mineral and the activator that we get fluorescence. So what about all these activators? What other impurities can be in our minerals? Well, in the Northwest where I live, there's a lot of iron and copper, and it actually dampens the fluorescent properties of our minerals that are out here in the Northwest. So we don't have an opportunity to find many minerals in the Northwest that will fluoresce because of that presence of iron and copper. Another property of the fluorescent minerals is that a lot of them will fluoresce just one color. However, some minerals will fluoresce a different color under a different wavelength. I've got a piece of optical calcite, which he calls an Icelandic spar, And in long wave, it's a kind of a purplish color, or a bluish color, I should say. And in short wave, it's more of a pinkish color. So that calcite will radiate a different color based on the energy that's put in to the base mineral. And it's interesting, this calcite spar, this calcite, optical calcite, has a double refraction, and you can actually polarizes light, and it was used in navigation by the Vikings. Okay, so fluorescent mineral properties. You know, there are a lot of minerals out there. Many will exhibit multiple colors with the same UV light on it. In this case, I'm got some willemite and calcite fluorescing. It's a zinc mineral from New Jersey. It's from the Franklin Sterling Hill district, and there are traces of manganese in this, causing the yellowish green colors to take place. Now here's a sample of a rock that's from the Purple Passion mine, and I've got 3 wavelengths: long, medium, and short. Displaying these on the slide, and you can see different colors illuminating based on the energy that I'm putting into that sample. All 3, and everything just glows very nicely. Here's some photographs I pulled off the internet of the zinc mine in Sterling Hill. You can see the references, the people standing in the tunnel that they've carved through here, and all the different colors: the green, the willemite, calcite here, zincnite in the blue. And another slide here showing some more colors. The hillside, they put a light on the hill, and you can see the entire hill from the outside light up. The reference there, you can see the guy standing there as he's standing right here. Here's the trees on top of the hill. Okay, so some more concepts of rocks glowing. There's a principle called timberescence, where it's a color that rapidly fades when it's exposed to bright light. You expose it to UV light, and it restores its pink color. This is a sample of sodalite. And I picked up some tugapite from I was lucky to get the door prize at one of the fluorescent meetings, and tugapite will do the same thing. It reverses color, changes color when exposed to UV light. Your transition eyeglasses are photochromatic, and same concept. It's a timberescence property of the silver salts that they impart into your eyeglasses. So when they make the glasses themselves, they put some purity silver salts in there, and this will darken when you go out in the sun, because the UV light turns that silver salts into a darker gray color. That's how your transition lenses work. When you're outside wanting to have sunglasses, and don't want to carry 2 pairs of sunglasses. So you're using the concept of timberescence in your sunglasses. Here's some other applications. If you have 2 pieces of quartz, the right kind of quartz, you can get triboluminescence. And I've tried saying triboluminescence several times. It's kind of rolls off the tongue after a while. This is triggered by mechanical action, where the electrons receive energy through mechanical action, and then will give off a glow. Thermoluminescence, you can heat or cool an item, it'll glow. Phosphorescence is the afterglow. This concept is where those electrons that were charged with energy take a long time to dissipate and go back to their grounded state. It's phosphorescence. It's an afterglow of luminescence. Bioluminescence, our picture of our firefly. We also have bioluminescence with jellyfish. There's kind of a story here. Bioluminescence is these living organisms actually create light through their chemical reaction inside their body and biology, if you will. My dad lived in Oregon most of his life, and he came to visit me when I was living in Virginia. And I said, "You want to go out and see the fireflies?" He said, "Oh, it's a myth." And I said, "No, it's not a myth." Went out and put a firefly in his hand, and it started glowing on his hand. And he said, "Oh my gosh, they're real." So I think that was kind of a fun story for me. Okay, chemical luminescence. Again, those little glow-in-the-dark plastic tubes. You break them, you get light from the chemicals that are embedded in those tubes. Cathode ray tubes. I worked at Tektronix, and the CRTs, the cathode ray tubes that we used in our oscilloscopes. That's the principal cathode luminescence. Electroluminescence. Those are the LEDs we have everywhere now, even in our headlights of our cars now. Okay, there's a story I'd like to impart on one of the minerals that actually self-collected. This one here, it's scheelite. I found it in an abandoned gold mine, actually, in Arizona. And this ore is called scheelite. It's a primary ore for tungsten, and it's used to harden steel. Well, in World War II was going on, the Far East cut our supplies of scheelite ore, and the war machine was going on. It was concerned that they weren't going to have enough raw material, to mine and refine tungsten. And so what happened was they discovered that scheelite and gold come up through the same processes. That's why when I went to this abandoned gold mine, I found scheelite. And these cracks of veins where gold comes up, there's oftentimes scheelite in there. Well, they discovered that shining a UV light on abandoned gold mines, and this is back in the days when UV lights, the late 40s, early 40s, I guess, they had to put these UV lights on big Jeeps and batteries, and it was a kind of a hard thing to do to get out there to the abandoned gold mines. But when they went out to the tailings of these gold mines, the entire ground lit up when they got these UV lights. And so it was very easy to discover large amounts of scheelite all over the United States, because these minerals are very difficult to discover. And with the use of UV lights, the ground, you can see these white spots in this sample, they just very bright under UV light. So we discovered that the United States had lots of ore, and the war machine could continue. Other applications for UV lights, we've got scorpion detection. You're out in the woods and you want to set up a tent. You may want to scope out your tent place before you go do it. There's just a whole lots of different applications. One application that I've used actually is identifying oil leaks. You can put a little UV dye in your oil, and you can find out where the leaks are coming around the seals. They use it for disinfection in the hospitals and sterilization, and you can also put it in water systems and kill the bacteria that causes algae and stuff. They use it for disinfecting water filtration systems now instead of other more expensive techniques. So I know the city of Malala is going to be using UV lights in their new water treatment facility. Okay, so the hobby. Well, it could be expensive. Some of these UV lights that are in display cases are pretty spendy. Depends on how big your budget is, what you want to do. You can get very inexpensive LED flashlights now, and they're actually available now in all three wavelengths. The short wave and the medium wave are a little more expensive than the long wave, but some of these are very powerful. They're very focused, and you can see your samples very nicely with these LED lights. And it's opened up our hobby tremendously to be able to go out and look for minerals that fluoresce. Our hobby has many organizations. The Fluorescent Mineral Society has a international bent to it, and there are many chapters in the United States and throughout the world. There's a database here, luminescence database. Also, there's a great teaching website called Nature's Rainbow, and I highly recommend, if you're getting into the hobby, that you examine this website. It's very good for understanding. There's a lot of archive material there, and that you may want to peruse. Not to be reminisce here, we want to make sure you understand the safety. The ultraviolet light's very hard you need to protect yourself. You don't want to get look at directly at a UV light. It's like looking at the sun. You burn your eyeballs and have serious injury. So don't look at these UV lights. Protect yourself. Use light glasses and to protect the UV light from hitting your eyes. Okay, so I wanted to, since I'm part of the Clackamat Rock and Mineral Club out of Oregon City, Oregon, we do a rock show. It's actually, I'm recording this video a week before our Memorial Day weekend, May 24th and May 25th, 2025. We'll put on a display of fluorescent minerals. There's a 16-foot table that we load up with all kinds of material, from fossils to glass to uranium to all kinds of minerals from in the display case. So here's an example straight on of some of the minerals that we have. And lastly, we have the grand finale of all the minerals from the Sterling Hill area up here exposed. It's just a very bright display.